In this video, we'll use the conservation of energy to help design a little bit a roller coaster, an amusement park ride where work is done to bring a car to the top of the first hill, and then the ride proceeds by going down a steep hill and up another hill and up another hill, maybe loops. We are only going to discuss the first hill and the second hill. So the characteristics of the roller coaster are given here. 48 meters is the height of the first hill. The cars are hauled up to that point by some mechanism in the roller coaster that we are not concerned with. At the top of this first hill, the cars have a speed of 2 meters per second. And I'm not going to provide the mass of the cars, but 2 meters per second. So they have some kinetic energy and they have some potential energy at the top of the first hill. As they go down to the first valley and up to the top of the second hill, in that whole process, this particular roller coaster has friction, and 15% of the initial sum of the kinetic and potential energy is lost. It's going to be energy loss due to the work done by friction. The top of the second hill is unknown, how high it is off the ground. The designers, however, want the cars to have a speed of 14 meters per second at the top of the second hill. So we're going to calculate the height of the second hill. So I'll make a crude drawing, label it here to help our discussion. We have some people on the ground watching the ride. The car at the top of the first hill traveling at 2 meters per second. First hill height, we go down a valley, and at the top of the second hill we're moving at 14 meters per second. So we have kinetic and potential energy at the top of the first hill. We have kinetic and potential energy at the top of the second hill, but we've lost some initial energy due to friction along the way. So let's go ahead and spell this out with some more symbols. Energy at the top of hill number 1, there's kinetic and potential. This supply of energy we're going to subtract from to determine how much energy we have at the top of the second hill. So 0.15, that's 15% of the initial energy is lost. Now putting in some numbers, we have the mass of the car, 1/2 mv squared is kinetic energy, mgh, g is the local acceleration due to gravity, h is the height of the first hill. Then we subtract off 15% of that same calculation, 1/2 mv squared plus mgh. That will equal then 1/2 mv squared at the top of the second hill, where the v is now 14 meters per second, and we have mg and h2 for the height of the second hill. We can cancel the mass of the car. If you inspect closely, you'll see that m, the mass of the car and the people in it, appears in every term. So mass here, a mass here, a mass, mass, mass. So we don't need to know the mass of the car and the people. Now I am going to find a number for each term, and you may want to pause this and bring out your own calculator and do this calculation, but 1/2 times 2 squared produces a 2. 9.8 times 48 produces 470.4. Remember the m has been canceled off. And then 15% of the sum of these two produces a negative term, negative 70.86. And then the 1/2 mv squared and the mgh, you should evaluate those. Pause this and evaluate those terms. Now we're going to combine the numbers together. I'm going to leave 9.8 times h2 on the right side, but adding the numbers, subtracting the 70.86, subtracting the 98, and to accomplish bringing the 98 term to the left side, I have to subtract 98 from both sides. Lastly, we divide by 9.8, and I find a height of around 31 meters, and that's 101 feet for the height of the ride. And there we have our design of a roller coaster using the principle of conservation of energy. We started at 48 meters high with some potential energy and a little bit of kinetic energy. We've lost some energy along the way. We have a kinetic energy that's from the given speed that we want at the top of the second hill. And then these are not energy terms because there's no mass, but that's where they come from. But that allows us, using the principle of conservation of energy, canceling off the mass, accounting for the work done by friction, to reduce our supply of energy, we're able to determine that the second hill should be 101 feet high, 31 meters. So if you have questions on this, you perhaps could rewind the video, play it again, ask your instructor. If you would like to see some other videos of physics and astronomy, short lectures and short example problems, these two websites are free, no registration. They have a list of the videos, semi-organized, so you can find them without a lot of difficulty. And Introductory Physics and Astronomy. If you do enjoy the videos a little bit, perhaps you would go ahead and subscribe to my YouTube channel. There's no cost for that, but while you're watching a video, go ahead and click on the subscribe button and keep practicing your physics problems.